All right, so now we begin Unit 1, which is technically called Chapter 3, and it's quadratic functions. Now, quadratic functions is going to be different from the math we had talked about in the previous grade of Math 10C, because in Math 10C, we basically dealt with just linear functions, or degree 1 functions. Quadratic functions are degree 2 functions, and we're going to introduce that quite quickly in this first part, or in our lesson 3.1. We're going to separate this into a few parts. So the first part is going to be getting to know this basic quadratic function of y equals x squared. And then what we can do with that y equals x squared is we can use a bunch of transformations or these different movements of this original function to put it in different parts of the Cartesian plane. Now, right away, when we look at this, we're going to break it apart into a part A, part B, part C. And these part A, part B, and part C's are the different type of transformations we can do, or translations or reflections that we can do. And we're going to really break that down in this lesson. Now, the first thing I really want you to be aware of as we're in this lesson is when we talk about a quadratic function and the basic quadratic function, it's y equals x squared. And from the previous grade, I had most of my students that I've taught before associate the fact that we say y is equal to this fx. So y and fx, these are equivalent forms. We can write these as equals to each other. So if you ever see these, they're interchangeable. They're used a lot interchangeably in this way. Now, in the piece below here, when we deal with this basic quadratic function of y equals x squared, the shape of this is actually a parabola. And so we're going to write that into our first piece. What is the shape? It is a parabola. All right. Now, does the graph open upwards or downwards? It opens upwards, and we're going to figure out more about why it does that. But for now, let's just write in that it opens upwards, and we'll get more specific about that very shortly. Why does the graph only lie in quadrant 1 and 2? Well, it's because it starts at the origin, and then it works its way up. So if you wanted to in your notes, I would just draw a little point at the origin here, and then have the arms going into quadrant 1 and the arm going into quadrant 2. So it opens upwards. Its lowest point is going to be this origin point, or 0, 0. And so we only have positive y values. There we go. So that's how I'm going to truncate that. And sometimes I use this positive or plus if just to represent positive. I mean, I could write out positive, but I'm just going to short form it. So we only have positive y values or only positive outputs. Therefore, it's only in this quadrant 1 and 2. All right. Now we're going to go over to our table of values here. And just using a bit of basic algebra, what we're going to do is take all of these x's and plug them in for x in this piece here. Okay, when we do that, here's what's going to happen. I take this and I'm like, okay, well, y equals x squared. If I plug in -3 for x, here's what it becomes, -3 and squared. Well, -3 squared is 9. And I'm going to repeat that pattern for all the rest of them here. So I'm going to write this as -2 squared is +4, -1 squared is +1, 0 squared, well, 0 raised to any power is just still 0. 1 to the 2, or 1 squared is going to be 1, and then 2 squared is going to be, in this case, 4. All right, now there's some interesting symmetry around here, and this is what I would have you do in your notes. I almost want you to group these 5 terms together. So you can kind of like group them however you want. You could put a bracket there. You could just put like almost like a highlighter squiggle down the line here. You could circle these ones, whatever you want to do. Just group these because these are going to be those 5 points that we're going to use to help us do the transformations in these different manners, or take this original function and shift it around depending on what the overall transformation is. Now, what are the 5 key coordinate points of this original function, y equals x squared or fx equals x squared? We're going to write those down. So starting off on the left-hand side, it's -2 and -4, or +4, I should say, not -4, because we're going to pull that from our table. The next point is going to be -1 and +1. Then we have 0 and 0, which is the origin point. We then have +1 for x and +1 for y. And our last point would be 2 for x, 4 for y. And these are coming directly off of the table that we had just constructed here, or the table of values. Now, what is the x-intercept and what is the y-intercept? Well, if this thing crosses through at the origin, well, let's even just draw a rough sketch of this before we go into the x-intercept, y-intercept, and domain and range, because it might help us see this quite clearly. So our first point, it's going to be on the origin. Our second point, 1, 1. Our third point is going to be 2 and 4, so I'm going to go up to here. Our next point is going to be -1 and 1, -2 and 4. And then we're going to draw the overlying graph on this. So you're going to go from the origin, connect all the points, draw an arrow with, or you're going to draw a line with the arrowhead on it, meaning that this extends infinitely in the positive direction upwards to y, and I guess in the x. And then we're going to go up like this, connecting all points on the right hand side, put an arrow on the end representing that this continues on to infinity. And from here, this is going to help us establish not only the domain and range, but what the x and y intercept is. My x and y intercepts, it's right here. If it crosses the x-axis here, this is where x equals 0. When we look at the y-intercept, it's where it crosses the y-axis, it's also at 0. And so for the x and y-intercepts, it's actually the same value. So we're going to go, what is the x-intercept? Well, the x-intercept is where it's equal to 0, and the y-intercept is going to be where y is equal to 0. Now, in terms of getting domain and range, well, domain and range in this case, for any sort of parabola that's going to face in this direction, whether it be up or down, we're actually going to say that it's XER or that it's all real numbers. And the reason is because these arrows extend outwards to the right to infinity, so they would just keep going on and on and on. On the left-hand side, same thing. These are just going to continue on and on and on to the negative values. So when we write our domain, domain being all of the possible x values on the graph, we're going to write d colon, we're going to make a bracket or this curly bracket and say x such that, or x based on these conditions where x is an element or is a part of the real numbers. Okay, so if it helps, what I would do is say for this bracketed term here, or for this piece here, if you're unsure of what this is, the vertical bar means such that, or given that these conditions occur. The x value, or x as an element of, when we see this e like this is saying an element of or as a part of. So just to kind of show this as a first time or as a reminder to you from the previous grades. Now the range, this is going to be a little different. It's going to have a similar element, but we look at this and we're like, if I look at my quadratic graph here, or my basic graph, I look and I see that it has a low point right here and then extends to infinity in the positive direction. What is this low point? It's where y was equal to 0. And so what we're going to do is we're going to accommodate for that. And then once it's past 0, it can be any number in the real plane. Y such that y is greater than or equal to 0, because it can exist at 0, but it must be above that. Once it gets past that, it can be any number in the real plane or is an element of the real numbers. Okay, now we're going to talk about the axis of symmetry, or the mirror line. The axis of symmetry is simply what line divides this graph exactly in half, or what line divides the parabola exactly to be symmetrical. So what we're going to do is we're going to put a dotted line right down this middle here, and we can clearly see when we do so that the left-hand side of this looks like the right-hand side. It's just the mirror image. And so we call this the axis of symmetry, and it's always defined in terms of x. So we say, what is the x value at this location? It's where x is equal to 0. Therefore, the equation of the axis of symmetry, which is this way of saying this, state the equation of the axis of symmetry, this is going to be where x is equal to 0. All right. Now, moving forward, we look at the vertex. And as a reminder, or maybe as something new to you, the vertex of the parabola is simply what is the value of the minimum point or the maximum point, or the coordinates for the low point or the coordinates for the high point. So in this case, we look at our basic graph, our basic quadratic function, and it has a minimum because it has a lowest point. What is the coordinate at this point? It's going to be 0 and 0. It was simply the origin point. So where x was equal to 0, where y was equal to 0. But often when we report this in terms of a minimum or a maximum value, we're just going to talk about it in terms of what is the y value. So let's fill in some blanks here. The vertex of the parabola is where the axis of symmetry intersects the parabola. Great, so it's that min or max value. What are the coordinates of this vertex? It is going to be 0, 0. 0 for x, 0 for y. Does it have a minimum or a maximum? It's actually going to be a minimum value for specifically this function, or the basic function. So the minimum value, we'll throw that in here. Hopefully I can squeeze that into here. The minimum value of the function is where y is equal to 0. Awesome. So axis of symmetry, we tell them what is the x value at the vertex. When we talk about the minimum or maximum value, we want to describe it using y's. All right, let's push forward here. Terminology. Let's just go through a brief sequence of these terminologies here. These are all really important. I would scan them closer as you review for tests, but just as we lead in here, we're going to go through them just one by one, just to make sure we're good as we move forward into the different transformations. So a quadratic function, this is something with a degree 2 polynomial. Degree 2 meaning that the exponent of the highest order is 2. So let's say I provide an example of a function f of x, and it's equal to x squared plus 2x plus 1. You've probably seen this before. So it's a regular trinomial, but we say this is degree 2 because our highest degree or our highest power is going to be this 2 in the exponent. And so that's what determines what the degree of the polynomial is. It's this leading one where we see if we have a 2 in the power, this is a degree 2 polynomial. All right, now next on this, general form versus vertex form. When we look at these two, these are two ways of representing the same data. One is the regular trinomial form we've seen before in Unit 1. The second one is where we can actually embed the vertex directly within the equation. And these will both be given to you on your formula sheet, so you do not have to memorize these. We're going to get quite an amount of work with these, but it's two ways of representing the exact same polynomial. Now, the graph of a quadratic function with a shape of these degree 2 is a parabola. So any quadratic function we're going to deal with in grade 11 here will always have this parabolic shape, which is that U shape, whether it be opening upwards or downwards. It's either going to have a minimum point or a maximum. Every parabola is going to be symmetrical about some vertical line, which we call the axis of symmetry. And remember, it's always a definition of x is equal to. So if you wanted to in your notes here, you could be like, oh, we always define it as x equals blank. Whatever that blank is the x value at which it's divided in half. Now, we go on to our x and y intercepts. You've probably dealt with this quite a bit in Math 10C. It's where it crosses the x-axis, where it crosses the y-axis. And then if we needed to solve for these things algebraically, remember, if I want the x-intercept, I set the y value to 0. When I want the y-intercept, I set the x value to 0. You always set the opposite value equal to 0. Now, just as a visual of what the axis of symmetry is, just in case you wanted to see it here, regardless of if I have a maximum, which is the second case, or a minimum, which is the first case, I look at this and I'm like, anytime I have the axis of symmetry, it's always that vertical line as defined by x is equal to some value that divides this as a symmetrical set of left and right sides. Now, we look at the domain and range. Domain and range, remember, if you don't know the distinguishing factor, domain is all of the possible independent variables. Well, or if we wanted to phrase it this way, the x values. The range will always be the dependent variable in the relation, which is our output, or it's our y values for these. And again, we want to look at, depending on the minimum or maximum, it has a huge implication on what this range becomes. Often though, in terms of the domain, like I said, we're going to always look at this and see it as x is an element of the reals, because on these parabolas, unless they're translated or unless there's a transformation that turns them on their side, we're never going to deal with this domain being anything other than XER. Or if the tails on the ends are fixed points or open points, we may see that we have to customize our domain, if you want to phrase it that way a little bit. But otherwise, it will always be XER. And this is a really common domain that we're going to be dealing with. All right, now let's go on to part A, which deals with what happens when we take this original function and then we add a q value. Now, we're going to see here that the original function of y equals f of x, or y equals f of x, which is equal to x squared, is shown to the right. So they give us the basic parabola over here on the right-hand side. Here it is. And I know it's a little faint, but there it is right here. And so it would include all those standard points like 0, 0, 1, and 1, negative 1 and 1, negative 2 and 4, and 2 and 4. Those are all like the traditional points we dealt with on that first page. And now what we're going to do is we're just going to adjust this formula just a little bit by adding some sort of q value. And we'll see what that means right here. Write an equation which represents the following alterations to the original functions. Again, we know that the f of x is equal to x squared for the original function. So anywhere I see f of x, I'm going to replace that with the x squared. Y equals x squared plus 3. And then in my second one here, I'm going to write this as y is equal to x squared minus 3. All right, and let's just do the same thing to get ahead of it. I want you to write that exact same thing below in terms of the graphing section, because we will use those very shortly. I just want to make sure that they're there if we're going to write them again. Okay, we go back up to here. So now we have these equations, and rather than f of x, it's now the actual function plus or minus whatever sort of q value we're going to put in here. Now what we're going to do is I'm going to make the first graph or the first alteration in red. I'm going to make the second graph or the second alteration in blue. Now, when we add a value to the original f of x function or subtract it, but let's focus on the adding here. When we add it, it means we're going to move all three or all of the units of y or all of the outputs up 3 units. So let's go do that over on the graph here. To get our second function or the altered f of x, I'm going to add 3 to all the y values. So if I started at the origin, now I'm going to be at 3, or 0 and 3 in this case. If I started at 1, I'm going to be up at 4. If I started at 1, I'm going to be up at 4. If I started at 4, now I'm going to be up at 7. And then if I started at 4, I'm going to be up at 7. Here is the new graph. Connect it with the tails and the arrows on the end, tail and the arrows on the end. And we're even going to get more specific. If you only have a pencil, I recommend you just label this. You say y is equal to, we're going to put x squared plus 3. Just to be very specific, because if you only have a pencil and you don't have any way to distinguish these by color, it might not make sense of like which function is which. I highly recommend you label them if you don't have multiple pencils. If you do, or if you have different colors, then this would be fine. What you can do is I would still label it just to be very clear in this. All right, we're going to do our second grouping here, or a second function alteration. So instead of adding 3, now we're going to subtract 3. That's going to take all of the original points and lower them down by 3, because we never go from the original to then a new graph to then another new graph. Well, unless they specifically request that, but in the case they don't, if they just say, hey, we're going to take that original function and minus 3, don't go off of the red graph, go off of that original graph. If I'm at 0, 0, now I'm going to be at 0 and negative 3. So I'm going to be down here. If I was at 1 positive, now I'm going to be at 2 negative. If I was at 1 positive, 2 negative. If I was at 4 positive, now I'm going to be down here at 1. And then lastly, if I was at 4 positive, I'm going to be down here at 1. Let's draw our tails with the arrows on the end. There we go. 1 and 2. Perfect. Try to make them as neat as possible. And then again, for clarity, let's label it. We're going to write this as y is equal to the x squared minus 3, or the original function minus 3 units. Now, we're going to clearly see that a specific pattern happened when we added a q value or when we subtract a q value. Whatever that value is, whether it's adding or subtracting, what this does is it's shifting the graph up or shifting the graph down. That's the effect of this q value here. So right when we go below, if we wanted to use our graphing calculator to sketch this, what we would do is, just to confirm that that's actually what happens and that's actually what we should be getting, I want you to go into your graphing calculators. I've given you each a cheat sheet for your calculator. You're going to go into your y equals, or if you have the Casio, you would click your menu key and then go into the graphing. Type this into y1, type the second function into y2. Now, for those of you that have the color calculators, this might look nicer. For those of you that have the black and white, no problem. You're still going to see the same sketch. It just won't be distinguished by color, so no problem. Now, obviously, if you need help with this, come see me. We will go through this and make sure you're all good, and we can access this. Now, I could show this on a graphing calculator here, but if you have the Casio, that's not going to help you much. So what I'm going to do is, in class, we'll go through this very specifically. Again, if you need help accessing this menu, just make sure you're good. We can do that. But at the end of the day, you should be getting a graph that looks like this, where you have one parabola that's a little higher, one parabola that's a little lower, and then if you didn't enter in the original function, you won't see that one. So don't worry about that. As long as you see your two curves, we're good. All right, now we're going to go down and generalize, and we're going to pick out some patterns from this or use some other functions to establish the patterns and how we can get the information out of these things here. So complete the following chart. In the top row, they give you the original function, y equals f of x. We know f of x in the quadratic functions unit is x squared because that's the original graph. Its vertex was at the origin. It's a minimum value because it opens upwards. And this is a y value. Remember, if they ask for a minimum or a maximum value, you could even write just above this table, this is talking about what is the y value equal to for that second value. So when we say a minimum of 0, it's the minimum of a y equal to 0. The equation of the axis of symmetry, it's always defined by x, and it's the thing that makes the graph symmetrical, x equals 0. Now, let's work with these next 3 examples here. I see y equals f of x plus 1. Well, I don't want f of x. I want it as y is equal to x squared plus 1. What is the vertex in this case? Well, if we went from 0, 0 and up a unit, now we're going to be at still 0 for x, but 1 for y. The graph didn't change direction of opening. It still opens up. So we're going to go minimum of 1 now because it's now at 1 for y. The equation of the axis of symmetry, well, it's still divided in half by this x equals 0. It didn't shift left or right. The graph only moved up or down. So it's still x equals 0. And then what is the description of the transformation? The units were 1 unit upward. Or you can just simplify it as 1 unit up. All right, let's go to the next one here. Y equals f of x minus 5. Well, we don't want f of x. Y equals x squared minus 5. What does this do? It shifts all units 5 units down from the original. So if we were at 0, 0, now we're at 0 and negative 5. It's still a minimum value because I haven't flipped the graph or I haven't reflected the graph. So it's going to be a minimum, but now it's at negative 5. We haven't shifted left or right, so the x equals 0 still. That makes this symmetrical. And then what is our description? It's 5 units, and I'm not going to put negative 5. I'm going to put 5 units down. There we go. All right, let's go to our last example in the table. Now, you might look at this and be like, wait a minute, y plus 4 equals f of x. Like, this is new. This will be more common in the 30-1 level. For us, all we're going to do is just move the 4 across using subtraction. When we subtract it across, it's y equals f of x minus 4. And now it looks like the other ones. So we're going to say instead of f of x, y equals x squared minus 4. Where does my origin go? Well, instead of 0, 0, now it's at 0 and negative 4 because I've gone down 4 units. It's still a minimum because we're not reflected yet. So we're going to put minimum of negative 4. We haven't shifted left or right, so it's still x equals 0. And then lastly, it's going to be 4 units down. So instead of 5 units down like the other one, now it's going to be 4 units down. All right. Now, let's generally describe what happens with the parameter. We kind of mentioned what happened based on the visual, but let's just make sure we put it into a sentence form. Based on the parameter q, what does it do to the original function or the original quadratic? It shifts the graph up or down. Either up or down. Now, shifting it up and down, that's not really the formal terminology for it, but shifting up or down, that's a description of the visual. What we want to do is right in this part 4 here, compared to the original function y equals x squared, the graph of y equals x squared plus q results in this is where we're going to introduce the formal terminology. What type of translation? It's a vertical translation because we're moving it up or down. So we call it, anytime there's a q either added or subtracted, it's a vertical translation. A translation is another way of saying movement in that direction, and it's of q units. So let's generalize. If q is greater than 0, the parabola will move up, or aka when q is positive, it will move up. If q is less than 0, or moreover, if it's negative, it moves the graph downwards, which we clearly saw when we were dealing with our blue and red graph, or even the table when we were doing the descriptions. All right, let's move on to part B. We're going to do a different type of transformation, or in this case, a different translation. Now, instead of adding a q value, we're going to talk about what happens when we shift the x value. And so we're not going to be dealing with anything y value. We're going to be purely looking at what happens when we alter the x value. So in this case, we have the original function f of x equals x squared. Now, we know whatever goes in the bracket here, this is what is entered to the function here. So if I see x right here, I'm going to see x in the function. Now, if I change that to something like x plus 3, well, here's what the function looks like, or here's what the equation looks like that would describe this graph. Instead of it being f of x plus 3, I'm going to make it y equals, anywhere I see the x, I'm going to substitute in x plus 3, which is the internal or the function. It's the input to the function, and then I'm going to square it. So we see how it goes from x squared to now x plus 3 squared. Whatever's in the bracket here, you're going to put in for whatever's in the x value. Now, for my next one, same idea. We're going to look at this as y equals f of x minus 3. I'm going to write it as y equals x minus 3 squared, where I subbed in the x minus 3 to the x value. Okay, now, again, we're going to make this one our red graph. We're going to make this one our blue graph. Okay, we're going to take the original function, which is y equals x squared, and we're going to do the following. Now, here's the trick around this one here. When you see plus 3 in the brackets, you're probably thinking, oh, we move each of the x values by a positive 3. It's actually the opposite. You need to pay attention to this. When you have this value, unlike the q where if you add it, you go up, and if it's negative, you go down, the x value is opposite of what you see in the brackets here. So if it's positive like it is here, we're actually going to subtract 3. And moreover on that in just a second. We'll discuss that in closer detail towards the end of this page, but always just trust me on this one. Whatever you see in the brackets, do the opposite. So if it's plus 3, we're going to go from the origin, which is at 0, 0 here, we're going to go to negative 3. So I'm going to put the new point right here. If I was at -1, now I'm going to be at -4. If I was at +1, I'm going to be at -2. If I was at -2, I'm going to be at -5. And then lastly, if I was at, in this case, I think our other value is 1, we're going to be at -1 here. There we go. And so this is us subtracting 3 units in the x direction from all of them. When I do that, now I can draw the line through or draw my tails with the arrows on the end. So one tail, second tail, draw those up. Perfect. As symmetrical as you can make this, the better. Really try to connect these with a straight line. My lines might be a little wiggly, but lots of you I've seen you do great with these, so don't worry. Okay, now we have our lowest point, which is shifted over by 3 units, and all of the units have been shifted. What we're going to do is we're going to do our blue graph now. So if +3 meant we went 3 to the left, when we look at the negatives, it's going to mean that we go to the right-hand side. So if you see negative here, I want you thinking, oh, I'm actually going 3 units to the right. So we take our original graph of 0, 0, and we move it to 3. We take our value of -1, and now we're going to be at +2. We were at 1, and now we're going to be at 4. We were at, in the original graph, -2, so now that's going to put me up to +1. And then we take our last point here, which was here at -1, and that's going to put us over. So, or apologies, I shouldn't be looking at this graph. I should be looking at this graph here. I'm going against my own word here. We were at +2. Now we're going to be at +5 here. And there's my point. All right, now again, we're going to draw our tails with the arrows on the end, our tails with our arrows on the end, or connect the points and then put our arrows on the end to represent that this continues, because the domain range wasn't set for us. They didn't tell us what value it goes to, so we just got to put arrows on the end. Now, here's our graphs. We have one that shifted to the left, one that shifted to the right, but they didn't shift up or down, and nothing else happened to the graph. Like, we didn't alter anything else. All we did was take each of the x values and shift them, and then we kept the y value exactly where it was. Okay, going down, using a graphing calculator to sketch this, well, in class, here's what you would do, whether you have the Casio or the TI, y is equal to, and instead of f of x, or f x plus 3, we're going to write this as x plus 3 squared. Like this, and then I'll be even more clear with this piece here. You're going to type that into your y1. Into your y2, or to your second function input, we're going to write this as x minus 3, all raised to the power of 2, or x minus 3 squared. When you graph this again, if you have the color calculator, it's nice because it will show you the 2 different colors. If you have the Casio or even the regular TIs, T84, what you're going to find is that these will just be black and white, but no worries, you'll still get the visual out of here. Now, just like we did for the vertical translations, now we're going to deal with the horizontal translations and deal with a table that gives us a bunch of different examples and what the effect on each of these are, or effect of each of the pieces we want to look more specifically at of the description of the actual graph. So when we talk about a replacement on the variable, this is just a fancy way of saying what is in the brackets that's connected to the f. So it's the function with the certain input. In this case, our certain input is x. So we're going to put, what is the replacement on x? Well, it's just x. Because this is the original function, you're not replacing x with anything. So realistically, you could even just put like a circle with a line through it, meaning there's no replacement. It's just the original function. If you want to put x there, good. Okay, then we look at it and we say all the other details are predictable. So the original function has a vertex at 0, 0. It opens up and has a minimum of 0. It's divided by x equals 0 because it's split down the middle at x equals 0, and it's the base graph. Now, for these next ones, what is the replacement on x? It's whatever's in the brackets, so x minus 2. So instead of it being y equals x squared, now it's going to be y equals x minus 2 all squared. What does this do? Well, it doesn't affect the y of the original vertex, but it does affect the x. So when we see a -2 here, it actually means that we went +2, or we went to the right by 2. What is the minimum or maximum value? It remains unchanged. So for actually all of these, because there's no sort of vertical translation, you could fill those in right away, or you could even just put like an arrow down like this, indicating that this answer applies to all of these. So I'm going to just do that. I'm going to put an arrow representing that the minimum of 0 stays the same for all of these, because we're not shifting up or down. We're just going left or right, which is affecting the x value of the vertex. Now, what is the axis of symmetry? I want you to, if you haven't done this, or maybe if you're not thinking to do this, what I would do in your notes is this: your vertex and your axis of symmetry, these two things go hand in hand. So whatever your vertex is, the x value of that vertex tells you what the axis of symmetry is. So instead of it being x equals 0, now it's going to be x equals 2. What happened to the original base graph? It moved 2 units to the right. So 2 units right. There we go. Now let's go to our third one in this table here. So what is our replacement variable? Well, it's x plus 5 because that was whatever was in the function notation. It's our input. I'm going to rewrite this as y is equal to x plus 5 all squared. If you see a positive 5 in here, please do not put, oh, it moves 5 units right. No, it's the opposite. Remember, with the q value or the shifting, the vertical translation up or down, it was exactly what you saw. For the x, it's going to be opposite, -5 and 0. The minimum value stays the same, so that's all good. In terms of our x value, it's going to be x is equal to -5, or the axis of symmetry, where it divides in half, is going to be at the vertex value for x, which is x equals -5, and then all the x values go 5 units to the left. All right, last one in the table, we're going to go down to where y equals f of x plus 7. The replacement on x is x plus 7, which is exactly what we find as the input. We look at this and we're going to rewrite our function as y equals x plus 7 all squared. What does this do to the vertex? Remember, if it's positive, it's actually negative. So now this is going to be -7, 0. Our I should say our minimum value is still y equals 0. So that will stay the same. Again, we're going to keep that. In terms of our equation of the axis of symmetry, it's always the x value of your vertex. So for here, we're going to go x equals -7. And then what does this do to the overall original graph? Everything moves 7 units to the left. So no sort of vertical transformation or no sort of vertical translation, but we do have horizontal translations. Okay, going below, let's summarize this. What is the effect of the parameter p on the overall original equation? Well, it moves the graph left or right, or we could say, just to match our terminology from the previous page, shifts the graph to the left or right. All right. Now, more formally, remember, because shifting the graph, that's not super formal, that's not super proper. What we want to do is actually give the specific terminology. When we have this p-value, it results in a horizontal translation. Translation being, again, just a movement of units. So we look at this and we say it is a horizontal translation of p units. Now, if p is greater than 0, which direction does it move? It moves to the left. It's actually the opposite. So we're going to say it moves left. For when it's less than 0 or when it's negative, I should say for p greater than 0, this is positive. So make sure you throw that in there. When p is positive, the graph actually moves left. When p is negative, the parabola actually moves to the right. Now, let's just actually show this. I said we were going to talk about this more right at the very end of the page, and here's why. Let's use these descriptions of p being greater than 0, p being less than 0, to show in the general equation why these end up moving left or right, or why are they opposite of what we think. So in the first one, if p is positive, I'm going to rewrite the equation as the following. Y is equal to the x minus, this is already in the equation. X minus already exists in the base equation. We don't, the minus isn't a result of us doing something specific. It is in the equation in and of itself. What I'm going to do is I'm going to put in a positive p and then square it. Well, what have we taught from previous grades? If I have a negative and a positive together like this, negative and a positive, this just becomes a negative. So this actually becomes x minus p all squared. Hence, when we have a p that is positive, what does it do to the graph? It actually moves it to the left. That's our connecting point here. Now let's do the same thing, but for a negative. When q value is negative, it's going to be x minus, in the bracket, a negative p value, all squared on the outside. Well, from our previous grade, again, what do we know about a double negative or two things of a same sign? It's going to become positive. So we could rewrite this as x plus p all squared. Hence, again, when p is negative, we end up having a positive here, which means we go right by that amount of units. And so this is a simple explanation of why we end up going the opposite direction. And I hope that helps and clears that up just a little bit. Again, if you need help with that, come see me for further explanation. But I would put this right next to both of these just so you're like, oh, okay, if I'm actually putting a positive in here, because the negative exists here, we move left. If I put in a negative, it's going to be the opposite because the negative and the negative are going to turn that positive. All right, now moving on to part C. This is our last transformation we're going to talk about for this section, and it's when we add this a value out in front. And so we've dealt with translations, whether they be vertical or horizontal to this point. Now what we have to do is talk about, well, instead of just shifting left or right, up or down, we could actually reflect this graph so we can flip the direction of the tails. We can also, in this case, make the thing wider or we can make it narrower depending on what happens. And so let's look at this very similar format here. We're going to take the original graph f of x equals x squared or y equals x squared, and we're going to put this a value in front and see what it does. Here's the equations. For this one, we're going to write our new equation, or the equation it becomes is 2 times, well, f of x is x squared. For the second one, we're going to write off to the side that this is y is equal to negative 2x squared because it's negative 2 out in front of the original function. And then lastly, we're going to write this as y is equal to 1/2 times the original function, which is x squared. Now let's represent all these graphs here. First one, just like the other two, we're going to do in red. Second one, we're going to do in blue. And then third one, we're going to do in green. And we're going to put these all together. So let's deal with the red first and foremost. Well, what does this actually do for us? In this equation, if we take the original x squared, or the output value, and we multiply it by 2, that's going to be our new value. So if I take 0 and 0, which is the origin point, and I multiply it by 2, well, I'm actually just at the same point. 2 times 0 just keeps me here. For my points at 1 and 1, here and here, if I multiply those by 2, they end up going to from 1 to 2, because 1 times 2 gets us to 2. Now, if I go into my other points in my standard form, which is at 4 and 4, you take both of these and you multiply them by 4. If you multiply 4 by 2, I should say, you're multiplying by 2, not by 4. If you multiply these 4s by 2 to get our new function or to get our new graph, this is going to put us at 2 and 8 and 2 and 8. Now, just like we've done before, I want you to connect those dots, put arrows on the end, try to extend those lines out as much as you can just to represent that it will continue going in this upwards / left and right direction, and that it will continue in this infinite pattern. Now, here's our first graph. Again, we would want to label this, so I think it's really important to go y is equal to describe the transformation here. So in this case, it's 2 times the x squared. Now we're going to go on to our next one, which is instead of it just being 2x, now it's going to be negative 2x. Here's the important thing about negatives, and we're going to make sure that we underline this or even highlight this. Highlight or underline the blue part, not the blue part, but the negative out front. And what I want you to write below is just this simple note to go with this. This is going to cause there to be a vertical reflection. So make sure you tie that together with that negative. There's going to be a vertical reflection if you see a negative out in front of this function like this. Now let's do this for all the values here. Again, we start at 0, 0. 0 times negative 2 just keeps us there. So the original point doesn't change. It's still on the origin. If I take the original points at 1 and 1 and I multiply them by negative 2, it's going to put me down at negative 2 here. So negative 2 and negative 2. If I go from my positive 4s, which were up here on the original function, positive 4 and positive 4, and I multiply both of those by a negative 2, it's going to go down to negative 8. And so we're going to go from our positive 4s down to negative 8 for both of those points. And again, just like we've done with all the other graphs, we're going to draw out our lines. What I do is recommend is just connect all of the points and then make sure you extend them a little bit, putting arrows on the end. So I may even extend this one just a tad at the bottom here, just to show that it keeps going on, put an arrow there, as neat as possible. And then what we're going to do is we're also going to label it with the function. Y is equal to negative 2 times the original equation of x squared. All right, so now we have this red graph, we have a blue graph. It looks like they did the same thing in terms of what they multiplied by, but again, it was a vertical reflection. It transformed it from being an upwards graph to now it faces downwards. Okay, lastly, we're going to do the green graph here. So we're going to take the original function and multiply it by 1/2. 0 times a half is going to keep us at the origin. If I take 1 and I multiply both those by half, it's going to put me at 1/2. If I take the original points that were at 4 and 4, or here and here, and I multiply those both by 1/2, aka I divide 4 in half, this is going to put me at 2 and 2. Now, again, we're going to put our arrows here, extend them out. I'm going to put my arrows here and extend them out. And then lastly, I'm just going to make sure I label it. Y is equal to, instead of it just being y equals x squared, now it's going to be 1/2 x squared. Okay, interesting. So not only did these graphs seem to transform their points, we saw that there was some sort of increase in these points or even a decrease given the green graph, but we also saw this reflection or this flip of the graph, which we hadn't seen yet. All we had seen was the graphs moving up or down, left or right. Now we're going to see that there can be a vertical reflection or that the graph can go from upwards or downwards. Using our graphing calculator, we can sketch these all. So when you put these into your graphing calculator under the y1, y2, and y3, which let me just provide that specific instruction down here. I'm going to go to this section and just provide a quick outline. In your y1, put 2 times x squared. In your y2, you can type in negative 2x squared. And here's a really important thing too. When you're putting in this negative, don't put the minus sign, put the little negative that's in brackets on your calculator because you'll get a syntax error. If you just type in minus here before the 2x squared, you need to put in the negative that's in brackets or the negative symbol, or else it gives the syntax error, like I was saying. Now for y3 or our third function, this is going to be 1/2 x squared. When you type all of these into y1, y2, and y3, you should get back to this where we have 2 of them that face upwards, 1 that faces down, or 2 that open up, 1 that opens down. All right, let's complete the following statements based on the general situation here. So compared with the original function, the a value of 2 in the original section that we dealt with, which was 2 times the x squared, it results in a vertical stretch about the x-axis of a factor of 2. It took all the y values and multiplied them by 2. And this is really common knowledge or common terminology you're going to see is when they say about a certain axis, what they mean is that it was stretching away from that axis or towards that axis. So if we go back up to our graph just to show you this, if I look at, let's say I was looking at 1 and 1 and it got multiplied by 2. Well, it moved away from the x-axis. In the case when we went 1 to 1 and we multiplied by half, it went down towards the x-axis. Vertical stretches are always either going away from the x-axis or towards the x-axis. So that's why we always say about that axis. Same with the reflection. If I multiply by a negative, it's reflected about this line because we went from facing upwards to then reflecting over this line to facing downwards like this. Okay, moving down here, the y-coordinate of each point was multiplied by a factor of, well, in the case it's 2 times the function, it's 2. The mapping notation, which is going to become very common as we move forward, especially in the 30 level, is we kept our x values the same, but we multiplied each of the y values by 2. So the original points were x, y, and if you haven't seen this notation before, this is always our original point. This is always the new point. So we go from xy to x and 2y. All right, compared to the original graph, if we took an a value of 1/2, well, a 1/2, this resulted in a factor or a stretch factor about the x-axis of 1/2. It multiplied each of the y-coordinates by 1/2, and therefore in the mapping notation, just like we talked about, if this represents the original, which I'll just kind of short form as orig, and this is the new, well, if each y value got multiplied by a half and nothing changed with if the x values stayed the same and the y values each got multiplied by 1/2, you're going to put x and 1/2 y in the mapping notation. Lastly, we're going to look at the example where we said if I multiplied everything by -2, or I put a -2 out in front of the original factor, or in the original function, I should say, not the original factor, but we multiply the original function by -2, it results in there being a vertical stretch about the x-axis of -2. We took each of the y-coordinates and multiplied it by -2, and the mapping notation is the following. We take this and we say, okay, it was x with 2, and I should make sure I have the -2 up front, -2 fx, which is another way of saying we have x and -2y, like this. So each of our y values was not only went from positive to negative, they also were multiplied by 2. All right, now looking at continuing our general trend here, when we take the original function and we put an a out in front, this results in a vertical stretch. So we're going to make sure we write that in here, vertical stretch. By a factor of whatever that a value is about the x-axis. So it's either stretching away from the x-axis or stretching towards the x-axis, getting closer. Summarizing that here, If a is greater than 0, meaning if a is a positive value, then the parabola undergoes a vertical expansion about the x-axis. The new parabola is going to look narrower because it's going to look larger. It's going to extend upwards. All the values get multiplied by some sort of value that's like, let's say 2 or 3. They all increase in this way that will make it that the graph turns narrower, which we saw in our example when it was the original black graph to the red graph or the black graph to the blue graph. If the value is between 0 and 1, meaning it's some sort of fraction, you could even write this in here. This means that if the value is some sort of fraction value, the parabola will undergo a vertical compression at about the x-axis, and the parabola looks wider. It almost looks flatter in a way. So when we say compression, what we're going to say is that this almost says that it looks flatter. It gets compressed against the x-axis and will flatten out. So that was our green graph, the one that was a little lower. It took the original graph and all the values kind of like flared out in a way. So in this case, and I should be highlighting these two as well. So if a was greater than 1 and it was positive, it meant that it was narrower. In the last situation, the parabola will look wider. It's flattened out. And then if a was less than 0, or if it was a negative value, the parabola is also reflected over the x-axis, and the parabola will open downwards. So that negative causes all of the y values to then flip from their original positive location to negative. The x's don't change, the y's do though. And because the y's change, we see this overall reflection about the x-axis or over the x-axis. Okay, let's complete a chart where we summarize this all together here. So we're going to take this and be like, okay, a value, the function, vertex, min-max, equation of the axis of symmetry, and a description. So we've done this 2 times before, but let's do that for these different a values. In the original function, the a value is actually just 1 because it doesn't change anything. So we have this 1, no matter if we multiply 1 to anything, it's going to stay the same, so it doesn't matter. And then all of the other details, pretty familiar to us. In the second case here, or in the second box, we look at this and see y equals negative f of x. The a value is negative 1. If there's no value here, what you can actually automatically do, just like you've done in previous grades, put a 1. Okay, what's the equation of the function? It's going to be y is equal to negative x squared. What happens to the vertex? Well, we saw it, that no matter what the a value was, it didn't change that origin point. So because there was no plus q, or there wasn't anything to like shift the graph left or right, we just looked at this and said, well, an a value, all it's going to do is just keep the vertex exactly where it is. So realistically, we could just even write 0, 0 for these ones and 0, 0 for these ones. No matter what value a is, it won't change the y value being 0. What is the minimum and max value? Well, we got to be a little more specific with this one. Rather than the graph look opening upwards in the case of it being positive, now this graph, if I was to draw a little picture of it, it looks like this. It opens downwards, it flips. So instead of it being a minimum, it's going to be a maximum, but it is still at a y value of 0. The equation of the axis of symmetry, well, it's still x equals 0 because we didn't shift left or right. And what is the description of it? It was reflected about the x-axis. Excellent. Okay, let's go on to our third case scenario here. We take the original function and we multiply it by 2. That means that the a value is 2. We're going to write this as y is equal to 2 times the x squared, which was our original graph. Again, multiplying 0 by 2 isn't going to change anything, so we're going to keep it there. This graph, if I was just to draw a tiny picture of it, it opens upwards still because it wasn't reflected. There was no negative, so it's still going to be a minimum and still be at 0. The graph wasn't shifted left or right, so it's just x equals 0. And we're going to say that there was a vertical stretch by a factor of 2 about the x-axis. I think that about the x-axis is very, very important. Because if you do not put about the x-axis, sometimes it's like, okay, what is it stretching about? Like, where is it moving in relation to? That's kind of a relative statement. When you say about the x-axis, it gives us context as to what type of axis is it moving away from when we stretch these points. Okay, now in terms of our last one here, or our fourth example, there's 2 things going on. First one, we see that there's an a value of negative 1/3. So we want to put that in here. What does this mean? Well, 2 things. the graph is going to flatten or be compressed. And then the second piece of this is not only is it compressed, but it's also reflected. So we're going to see a graph that would look kind of like flatter like this, but also open downwards. So the original function is going to look like the following. Y is equal to -1/3 x squared. That's not going to change the fact that the y value is 0 because -1/3 times 0 is still just 0. In this case, we're going to have a maximum value because the graph was reflected about the x-axis. The x value is still going to be equal to 0 for the axis of symmetry. The graph wasn't shifted to the left or the right. And then what we're going to say here is we're going to say a vertical stretch by a factor of 1/3 about the x-axis. Additionally, we want to say that there was a vertical reflection about the x-axis. So two things going on there. Not only was it vertically stretched, but a vertical reflection because of the negative. Now, instead of a vertical stretch, what you could do is you could talk about it being, so we said reflections and vertical stretches. There was this language that they used above, which I'm a fan of too. So if you want to use this as well, vertical expansion about the x-axis, meaning it grows about the x-axis or it's growing vertically, or you could talk about a vertical compression. If you wanted to use that language here instead, that would be totally fine. So in this one, let's say I go to the example where it was multiplied by 2, you could say that this was a vertical expansion instead. So I'm just going to fill that in here, that this is an expansion. And then when we talked about it being this 1/3, this was a vertical compression. Perfect. And then again, that terminology comes from above here, where if we look at this piece here, we're like, okay, expansion means it's going to be multiplied by some value that's greater than 1. If we have a value that's between 0 and 1, it was a compression. It gets flattened. It gets pushed against the x-axis. But I'm fine with you just saying a vertical stretch by this factor about this axis. That's also equally okay. So the one in red is just another option you can use. Okay, this is where you move into the check your understanding. Now, what I'm going to recommend is I'll post this solutions on D2L. It will be included in the lesson notes. But what I want you to do is I want you to take it away from here. Try it out based on your understanding from the lesson. See what you can do with these. See if they're being vertically compressed, stretched. Are they being translated horizontally, either left or right? Are they being translated either up or down? You tell me that and then give me the equation in terms of the general form. So this will be where you can kind of put it all together and use the lesson notes to help you out. All right, good luck.